Okay, so good afternoon, class. So we come now to the part 2 of the topic in power plant engineering. So this is fuels and combustion. So last time we already discussed some definitions and terms involved in fuels and combustion. So we already discussed specific gravity and degree EPI and other definitions. Okay, so let us now come to the viscosity. Okay, so viscosity. So this is a measure of the resistance of the fuel to flow. Okay, so measure of resistance to flow. So meaning, so as the oil may be flow inside a pipe, the tendency of the oil which is uh, flowing at the surface of the pipe is slower as compared to the part of the oil flowing at the center of the pipe. Okay? So, the more the viscosity rating of the fuel or oil, the more the viscous the oil. Okay? So, we have here two types of viscosity. So, one is the so-called absolute viscosity. So, what is this absolute viscosity? So, this is defined as the unit of force required to move one layer of fluid at unit relative velocity to another layer of fluid, which is at unit distance from the first. Okay, so as what I have said, so the liquid or the oil moving uh, in a surface is slower as compared to the oil flowing at the center of the pipe. Okay? So, the kinematic viscosity, so this is defined as the ratio of absolute viscosity divided by its density. So, after knowing the absolute viscosity and then divide it by the density, we now obtain the so-called kinematic viscosity. So, what are those units used in this viscosity? So, for absolute viscosity, we have the Rhine. So, this is in English. So, Rhine is pound second per square inch. And another, we have the Poise unit. So, this is in CGS. So, that is dyne second per centimeter square or Pascal seconds. Okay? So, for kinematic viscosity, we have a unit of Stoke. Okay? So, 1 Stoke is equivalent to 1 centimeter square per seconds. Okay? That is equivalent to 0.0001 square meter per second. So, take note, the commonly used units here is the centipoise and centistokes. Okay? So, another, we have the Sabol viscosimeter. So, this is the instrument used in order to uh, identify the viscosity. Okay, so this measures the time required for a given quantity of oil at standard temperature to flow through a specified tube or orifice. Okay, so determining the time. Okay, so another, we have the SSU or the Sabol second universal. So obtained by timing the interval required for a 60 cubic centimeter of oil to flow through tube or pass through a standard orifice. Okay? Take note, 60 ml or 60 cc of oil. That is the standard uh, oil, which is required for testing. Okay? So, we have here conversion for synthestocks. So, that is 0.308 SSU or the Sabol second universal minus 26. Or, we have here the viscosity equivalent to 0.22 SSU or the standard second universal minus 180 over SSU. So that is defined in synthestocks. Okay? Another is we have the Sabol second furol. Okay? So unit used for very viscous liquid. Take note, very viscous liquid. Or another, we have here 62 SSF is equals to 600 SSU. That is another conversion of the viscosity. Okay? So, we have here the properties of oil. Okay? One is plus point. So, what is plus point? The temperature at which oil gives off vapor that burns temporarily when ignited. Okay? Gives off vapor. Okay? So, when ignited, the vapor will temporarily burn. Okay? Another is the definition of plus point. So, this is the temperature to which oil must be heated to give off sufficient vapor to form an inflammable mixture with air. Okay? Another definition, the temperature at which ignition of the fuel vapors rising above the heated oil will occur when exposed to an open flame. Okay? Another, we have fire point. So, fire point is the temperature at which oil gives off vapor that burns continuously. Take note, continuously when ignited. Okay? So, from the word fire point. Okay, fire. Continuously when ignited. Another is pour point. So, this is the temperature at which oil will no longer pour freely. Or the temperature at which oil will solidify. Okay? Another is dropping point, temperature at which grease melts. Another is cloud point, the temperature at which the paraffin elements separate from oil. Another, we have the Conradson number or carbon residue. So this is the carbonaceous residue remaining after destructive distillation expressed in percentage by weight of the original sample. Okay? So another, we have the viscosity index. It indicates the relative change in viscosity of an oil for a given temperature change. Another is octane number. The ignition quality rating of gasoline. Ignition quality rating of gasoline. Okay? So, which is the percentage of volume of isooctane in a mixture of isooctane and heptanes that matches the gasoline in anti-knock quality. Okay? Another is cetane number. So, this is for diesel. So, the ignition quality rating of diesel, which is the percentage of cetane and the standard fuel. Okay? Another, we have the aniline point. So, it's the temperature where equal parts if oil and aniline will dissolve in each other. Another is volatility. So, it's the ability of a liquid fuel to change into vapor, which is manifested in the temperature range to which various portions of the fuel are vaporized. Okay. Another, we have here now the composition of fuels. Okay. So, paraffins. That is CN H2N plus 2. So, take note, this is for hydrocarbon fuel. So, saturated hydrocarbons. Very stable in characters. Another is the olefins. Okay. This is C2H2N. Okay. So, unsaturated hydrocarbon. So, characterized by the presence of a double bond between carbon atoms. So, take note, if we look at the formula, so the the number of uh, atoms in carbon is doubled in the hydrogen. Okay? So another is diolefins. Okay? So that is CN H2N minus 2. So less saturated than olefins. Okay? Another, so we have here the analysis of fuel. So analysis of the composition of fuel. So we have here, so actually this analysis is divided into two. We have the proximate analysis and the other is the ultimate analysis. So what is a proximate analysis? Okay? Proximate analysis is made by heating the coal until it decomposes successively in the three of the four complex items of proximate analysis. Okay, so the four is found by the difference by the difference. So a typical proximate analysis of coal determines the percentage of moisture. Okay, take note. Percentage of moisture, volatile matter, fixed carbon, and ash. So this only defines four. Okay, one is the fixed carbon, volatile matter, moisture, and ash. Anyway, so let us divide or define this for constituents. So moisture. Okay, so this is determined by subjecting a 1 gram sample of coal to a temperature of 220 degrees Fahrenheit to 230 degrees Fahrenheit for a period of exactly 1 hour. Okay? So, that is determining how you are going to get the amount of moisture in a carbon sample. Okay? Another is the volatile matter. So, consists of hydrogen and certain hydrogen-carbon compounds that can be removed from the coal merely by heating it. Okay? Another is ash. This is performed by heating the same sample of coal used in the moisture determination to a temperature of 1,290 to 1,380 degrees Fahrenheit in an uncovered crucible. So, with good air circulation until the coal is completely burned. Okay? Another is the fixed carbon. So it's the difference between the sum of the percentage of moisture, ash, and the volatile matter. Of course, the complete sample is equivalent to 100. Okay? 100% less the percentage of moisture, ash, and the volatile matter. Okay. Another, we have the ultimate analysis. So, this defines everything. Okay? So, analysis of composition of fuel which gives on mass basis. Take note, mass basis, the relative amounts of carbon, hydrogen, oxygen, nitrogen, sulfur, ash, and moisture. So, any elements involved and the fuel is defined here in ultimate analysis. Okay, so let's now go to the basis of reporting analysis. One is as received or as fired. Two is dry or moisture free. Three is moisture and ash free or combustible. Moisture, ash, and sulfur free. Anyway, so in the other presentation, we are going to take an example of this. So in order for us to be familiarized with the reports of the analysis of the coal. Okay? Another is the heating values of fuel or calorific values. So this is also divided into two. So one is the higher heating value or gross calorific value and the lower heating value or the net calorific value. So what is a higher heating value? The heating value obtained when the water and the product of combustion is in liquid state. Take note, higher heating value, the water and the product of combustion is taken in a liquid state. So, but for lower heating value, the water and the product of combustion considered is in a vapor state. Okay, so take note of the difference between the higher heating value and the lower heating value of the fuel. Okay, so let us now go to the methods of determining the heating values. Okay, so anyway, there are two. Okay, so we have here the bomb calorimeter. So of course, this is used for solid and liquid fuels, and the gas calorimeter for the gaseous fuel. And we have here the formula or the Dolong's formula. This is an empirical formula used for determining the ultimate analysis of fuel. So take note, higher heating value. Okay, higher heating value is 33,820. So take note, this 33,820 is the heating value of pure carbon. Okay, multiplied by, so this is multiplied by C here. So it was omitted. Plus 144,212. This is the heating value of a pure hydrogen. So minus, or hydrogen minus oxygen over 8. So of course, the oxygen is subtracted rather, because it is not combustible. Okay? So plus 9,304 S or sulfur. Okay? So take note that the unit of this formula is in kilojoules per kilogram. And then changing this to English units. Of course, 33,820. So this is making this in BTU per pound. So divide this by 2.205 and 1.055. The result is 14,600. Same as with 144,212, dividing this by 2.205 and 1.055. So that is 62,000. Okay? So this is now in BTU per pounds. Okay? Okay, so we have also here for ASME. Okay? American Society of Mechanical Engineers. Okay? ASME formula. So we have here also the heating value. So this is in terms of the degree API. So this is formula for petroleum products. Okay, so this is 41,130 plus 139.6 degree API. So this is kilojoules per kilogram, or in English that is 17,680 plus 60 multiplied by degree API. Take note, class, the original formula here is the English units, which is BTU per pound. So this 41,130 plus 139.6 is derived from this English formula here below. Okay? So another we have here for the Bureau of Standards. So we have here the higher heating value is equals to 51,716 minus 8,793.8. Take note, class, that the parameter considered here is the specific gravity. Okay? So take note, if only the specific gravity is known, use this Bureau of Standard formula. Okay, so this is in kilojoules per kilogram. And then, that is, we have here also below the formula for English units. Okay? So, let us now consider the difference between the higher and lower heating values. Okay? So, the difference between higher and the lower heating values is equals to 9 multiplied by hydrogen multiplied by 2442. So this is in SI units. And in English, HHB minus LHB is equals to 9H. And then changing 2442 to English and BTU per pound. So that is 1050. So where this 9 hydrogen here is the pounds of or kilogram of water formed per pound or kilogram of fuel burned. Okay? And 2442, of course, this is the latent heat of vaporization of water. And H2 is equals to 26 minus 15 multiplied by the specific gravity. This is now in percentage by weight. Okay? So we have now here the composition of air and molecular weights. Okay? So we have here composition by weight. So that is 76.8% nitrogen, 23.2% oxygen. Take note, this is the composition of air. Okay? So that is equivalent to 76.8 divided by 23.2. That is 3.3 pound of nitrogen per pound of oxygen. So another we have here by volume. So this is 79% nitrogen and 21% oxygen. Okay? So, or the ratio of this is equivalent to 3.76 moles of nitrogen per moles of oxygen. Take note, class. This is very important in balancing of equation and combustion of fuels. Okay? So, another, we have here the molecular weights. Take note, for air, that is 29 or 28.97 kilogram per kilogram mole. Okay? So, use 29. Okay? Here. So, round off the values 28.97. And then the molecular weight of carbon, so that is 12. So, that is 12 kilogram per kilogram mole. And for hydrogen, this is 1. So, multiplied by 2, that is 2 kilogram per kilogram mole. Another is oxygen, 16. And then, times 2, we have here 16 times 2 is 32 kilogram per kilogram mole. And for nitrogen, we have here 14. Multiplied by 2 is 28. And for sulfur, we have a value of 32. Okay? So, we have now here the air-fuel ratio or the theoretical air-fuel ratio. So, take note. So, determining the theoretical air-fuel ratio if the ultimate analysis of the fuels are known. Okay? So, this is 11.53, meaning if you are going to burn a pure carbon, it requires 11.53 parts of oxygen rather. Okay? So, that is WTA or the theoretical air fuel ratio is 11.53 carbon plus 34.36, or sometimes they use 34.5, and then this is sometimes 11.5, and then multiplied by hydrogen minus oxygen over 8 plus 4.29 sometimes, or 4.3 sulfur. Okay? So, take note, WT is the theoretical air-fuel ratio in pounds per pound or kilogram per kilogram. Okay? C is carbon, H2 is hydrogen, O2 is oxygen, and S is for sulfur. Okay? So, another we have here, the actual air-fuel ratio. Okay? So, actual. So, take note, we are only going to multiply the theoretical air-fuel ratio plus, multiplied by 1 plus the excess air given. Okay? E. So, that is now the actual air-fuel ratio. Thank you very much, class. Actually, we now already discussed several formulas which is very important in calculating fuels and combustion. Okay? So thank you very much, class.